Hello, everybody, and welcome back to Latin Crypt 2021, and welcome everybody to the second invited talk. As in the other sessions, please write your questions below the video, and they will be answered during the talk or also after the talk, depending on your questions. But now it is my great pleasure to introduce our speaker today and welcome Shweta Agrawal. Shweta is a renowned researcher in cryptography and information security. And her works include, but is certainly not limited to, constructing different advanced encryption schemes such as homomorphic, functional, identity-based, deniable, or broadcast encryption. Mostly the constructions are from Lattices, and from her for her work about the broadcast encryption scheme, she also received the Best Paper Award of Eurocrypt 2020. Shweta spent much of her academic career in US American universities, including the University of Texas in Austin, Stanford University, or the University of California in Los Angeles. Today, she is an associate professor at the Indian Institute of Technology in Madras, and she is also a Shweta Jayanti Fellow. Now, I'm very excited to learn Shweta's take on recent progress and challenges in lattice-based crypto. The virtual stage is yours, Shweta.
Thank you, Nina, for the introduction, and thanks to the organizers for inviting me. It's my great pleasure to be here. Although, as I was saying to Valerie just before, that being invited remotely to South America is really a little bit of a bummer. So maybe I can follow it up with a physical invitation later. All right, so I'm going to talk about recent progress and challenges in lattice-based cryptography. And needless to say, this is a very, very wide area of research. And it's not going to be possible by a long shot to talk about everything that's cool and exciting and going on in this field. So just for the purpose of a very zoomed out view, I've come up with these three different colors. So the red is the stuff that we would love to know, but we don't know how to do with lattice crypto. And this includes fundamental primitives like indistinguishability, obfuscation, functional encryption, deniable encryption, broadcast encryption, witness encryption, constrained PRFs, and so on. Then there are things in the yellow, which is stuff that we know how to do, so it's feasible. But at the moment, it's very far from practical. So these constructions are going to be very, very slow and not ready to be deployed. So this is, non-interactive zero knowledge, which is a great result that we had recently. Lockable obfuscation, homomorphic signatures, traitor tracing, and also general fully homomorphic encryption. And then we have stuff in the green, which is actually practical from lattices, right? So here we have our favorite primitives like public key encryption, signatures, commitments, and restricted forms of zero knowledge for particular algebraic statements. So you can see the NIST competition is full of entries from lattices for these primitives. And for the purpose of this talk, I thought that I'd focus on indistinguishability obfuscation and its closely related primitive functional encryption, because there's been a lot of exciting work in these areas recently, and also in the lattice domain, there's a lot of very interesting work that remains to be done. Okay, so this is going to be the roadmap for my talk. We'll start out with understanding these primitives that we're trying to build. We'll look at some of the progress that we've seen in the last few years. And then we'll look at what are the challenges in getting these primitives from lattice assumptions. And we'll end with some open problems. As Nina said before, I'll be more than happy to answer questions as and when you think of them. So please feel free to interrupt and ask questions anytime during the talk. All right, so let's start with defining the primitive of obfuscation. So first, at a very high level, let's just motivate the idea, right? So let's say that we have a smart student here at IIT Madras, and she comes up with a better algorithm to factor numbers. Now, she could write a paper and win the best paper award at crypto, but maybe she's more entrepreneurial, and what she'd like to instead do is keep the algorithm secret and sell its functionality. So she would like, in particular, to input her code to some kind of compiler that outputs a garbled or an obfuscated version of the same code. So in particular, this obfuscated code should still work correctly. It should have the same functionality as the original program, but it should have some kind of strong guarantee that the algorithm that she's coded into it is secret, right? Because she doesn't want that to be leaked. So the box that's going to let us do this at a very high level is known as an obfuscator. And a little bit more formally, what we're interested in is to compile a circuit C into a different circuit C hat so that C hat preserves functionality. So as we see in this picture, for any input X, the two circuits yield the same result and satisfies some kind of security, right? So it should be unintelligible and we'll have to define this, right? So what do we mean when we say it is unintelligible or hard to reverse engineer? So the definition we're going to use was suggested in 2001 in a seminal work by Barak et al. And the question that we're asking is the following. Let's say you have two circuits which are actually equivalent. So what do we mean by equivalent? Well, they should have the same size and they should have the truth table. So let's say that the adversary can see two circuits that are equivalent in this way and can see the obfuscation of only one of the two circuits chosen at random, then the adversary should not be able to figure out which of these two circuits was obfuscated. And a moment's thought reveals that if you don't care about efficiency, then in fact this problem is trivial to solve. How? Well, just output the truth table or output some canonical representative of the class of equivalent circuits, right? So if you didn't have any time pressure, then this is an easy problem to solve. But if you do want your compiler to be efficient, then this problem turns out to be very difficult. And our goal for today is to see if we can construct such an obfuscation scheme. All right, so before we proceed, for those of us who have not seen this definition before, it may not be immediately obvious why we care about this definition, right? So at least at first glance, I think this definition seems to be more or less useless. We already know that the two circuits are equivalent. So really, does it matter which particular representation you use? I mean, the adversary knows everything except the bit of which of the two circuits is obfuscated. And moreover, these circuits are equivalent. So what is this really good for? And as I already said, it's not clear if we have applications for this primitive. But as many of you probably know, over the last several years, we've seen like a plethora of really surprising and cool applications of indistinguishability obfuscation, or IO as we'll call it. And sort of very broadly, we can say that IO is, at the moment, almost crypto complete. So practically everything that you can think of, IO often gives you a way to realize it. Okay, and this is by now, as I said, well known. So, starting with uh, basic primitives like public key encryption to more advanced things like functional and deniable encryption, FHE without circular security, witness encryption, multi-party non-interactive key exchange, so on and so forth. The list goes on. So, there's not enough space in a slide to fill all the applications of IO. And this was very surprising. At least to me, it was very surprising that this object should have so much utility. So, okay, we agree that this is something useful to have. So how do we go about building it? So at a very high level, there are roughly two approaches that we've seen in the community. The first is the so-called direct constructions, and the second is what we call bootstrapping based constructions. So let's see what these are. So direct constructions are all based on a mathematical object called multilinear maps, which we'll define in a second. And we have candidates of these multilinear maps from lattices. Okay, so that's great because we can hope for it to be post-quantum. But these direct constructions have had a little bit of a, tumultuous history. So there have been many attacks and then fixes and then more attacks and then fixes and so on. It's been hard to understand security. And then we have bootstrapping based constructions where the construction idea is to reduce the functionality and security of IO to something smaller and smaller so that you can hope to just instantiate the smallest piece in some way. So you keep trying to simplify the problem. So let's look at both these approaches in a little bit more detail. So first, in order to define multilinear maps, let me just remind you what bilinear maps are. And these, of course, have been used enormously in cryptography. I'm sure you've seen this before. A cryptographic bilinear map gives you two groups, G1 and G2 of some order, and a map, which we call E, from G1 cross G1 to G2, such that for all A and B in ZP star, E of G1 to the A, G1 to the B is equal to G2 to the AB. So essentially, you can think of G to the A as an encoding of A, where A is going to be hidden by the discrete log problem. And similarly, you have an encoding of B, and essentially this map is letting you do one multiplication in the exponent, right? So that's the functionality that you get. And the hardness guarantee that you have is that, well, functionality lets you compute degree 2 polynomials in the exponent, right? So we already saw that you can get G to the AB in the target group, which is G2. And if you have, let's say, an encoding of C, then you could certainly get an encoding of AB plus C. So you can certainly add stuff and you can do one multiplication. So you can compute degree 2 in the exponent, and the hardness, the bilinear Diffie-Hellman assumption says that degree 3 should look random. Okay, so degree 2 you can do, and degree 3, not only can you not do it, you cannot compute a degree 3 polynomial, but you cannot even distinguish a degree 3 monomial in the exponent from a truly random element in the group. Okay, so in the relevant group. So this is what the hardness assumption says. And we have an efficient instantiation of these bilinear maps using Weyl or Tate pairings over elliptic curves. So that's great. I mean, there was quite a boom of crypto that came out of these bilinear maps. I mean, they've been amazingly powerful, very, very useful. So everything is great. And sort of contemporary to bilinear maps in some sense, the notion of multilinear maps was already thought about. So already in 2003, Bonnet and Silverberg talked about multilinear maps and what they'll be good for. Let's quickly define them. It's a very natural generalization of bilinear maps, right? So in bilinear maps, we saw that you could do degree 2 computation in the exponent. Now we just extend that idea to polynomial degree. So now instead of one map, you instead have a family of maps over, a sequence of groups, and you can use this map for any two groups. So your map EIK goes from GI cross GK to GI plus K. And it does, the same thing that we saw in the bilinear setting. But the crucial difference is that you don't have to stop. So you can keep going, right? And the hardness that you would like is that, well, at least discrete log in each group should be hard. And you'd like a sort of generalization of the bilinear Diffie-Hellman problem that we saw, which is to say that if functionality allows you to compute degree n, then degree n plus 1 should look random. All right, so this is, the notion of multilinear maps. As I already said, applications were described as early as 2003, but the community has become a bit pessimistic about the existence of these maps in algebraic geometry. So to the best of my knowledge, there's been a lot of effort to construct these, but we haven't succeeded. However, a sort of relaxation of these, perfect multilinear maps that we talked about, the so-called noisy multilinear maps, were constructed in a breakthrough work by Garg Gentry and Halevi in 2013. And this construction was based on ideal lattices inspired by N-true. Okay, so again, we are happy because lattices are back in the picture. And well, though they were noisy multilinear maps and not the exact maps that we wanted, they still turned out to be immensely useful. They could be used to build IO, and they had many more applications. So given the history of make, break, and make again, it's natural to ask, where are we with these multilinear maps at the moment? And we still don't have candidates of clean multilinear maps, which we wanted. For noisy multilinear maps, we do have candidates, as I already said. All of these, in the most general sense, have been broken, unfortunately, using a large class of linearization attacks. But there has also been progress in fixing them. And the latest that I know is that there are these works that show candidate constructions for multilinear maps that are secure against all known attacks for multilinear maps. So they define a model which captures the weak multilinear map model, which captures all known attacks on these objects, and they have a candidate that is secure in that model. So these are not broken yet. So this is perhaps not so satisfying, but at the moment, this is the best we've got. So nevertheless, assuming that we have polynomial degree multilinear maps, we do get IO. And this is the sort of so-called generation 1 of IO. Okay, so from poly degree maps. And an obvious and important open question is, can we build these maps from lattices with better understanding of security, better guarantees? All right, now let's look at bootstrapping based constructions. And here the idea is, as I already said, reduce, reduce, reduce. So what is the minimum functionality that you need? How much can you clean up assumptions, right? So there was a sequence of works that reduced the degree of the multilinear map from polynomial to just constant. And this gave us generation 2 IO. So this is from constant degree maps. And these constants started out being fairly large, like maybe 30, and they went down to 3 in the work of Lint SRO 17. Then we have generation 3 IO. So here the idea is that, look, I don't have a degree 3 map. I don't know how to get it. So I'm going to actually hold my degree 2 map as an invariant, and I'll adjust elsewhere. So what these generation 3 IO constructions do is that they use potentially degree 2 maps, or maybe no maps at all, and they try to reduce the missing piece to something smaller and smaller, and they instantiate that using a heuristic component. But nevertheless, though we've made a lot of progress, these constructions still have heuristics in them. Okay, so that's generation 3. And then generation 4 actually manages to make much more progress on these heuristics. And in particular, there is this recent breakthrough work, which I'm sure most of you know about, of Jane Lin and Sahai from this year, which shows how to actually remove the heuristics altogether. So by very carefully and cleverly combining a sort of a set of different assumptions which seem unrelated to begin with, they manage to get IO from standard assumptions. So that's really a big step forward. The others also make a lot of progress. So in particular, the main advantage of the other candidates here is that they don't use pairings. So no maps. So in particular, you can hope that they'll be post-quantum secure. But so far, they still do have some non-standardness. So for instance, for constructions that are using LWE, they assume some kind of circularity. So we're not going to go into details of this, but there's still work to be done here. Okay, so obviously, I guess a very obvious and fairly significant open question is whether you can have post-quantum IO from standard assumptions. So, don't use pairings and use something else which is post-quantum secure. All right. Now, this was just a very quick overview, and for the rest of the talk, I'm going to actually try to construct these together. Okay, so post-quantum IO with provable security, what approaches do we have, right? So one approach is via the notion of functional encryption, which I'm going to define in the next slide. And then we have another approach using a weakening of functional encryption called functional encodings, or a close variant succinct randomized encodings. And using these, you could get IO as well. Or you could use FHE with some additional properties. So this is also a very promising line of work. So, circularity assumptions on FHE. So for the rest of the talk, I'm going to just focus on one of these approaches, the first one of functional encryption, because I feel that there's more work to do here than in the others. Of course, there's work everywhere, but just for the sake of choosing one. Are there any questions so far? All right, so I'll keep going. So
no, so far there are no questions from the audience. Thank you.
Okay, thanks. So let me keep going. So let's start by defining functional encryption. Functional encryption is a generalization of public key encryption, which allows partial decryption keys. Okay, so your encrypt algorithm can take some input X and produce a ciphertext. Your key generation now is not just going to, unlock the ciphertext and get X. I mean, it's not just going to give you a key that unlocks the ciphertext and gets X. It's actually going to give you a key corresponding to some function. And when you decrypt this ciphertext with this secret key, you're supposed to just get f of X and nothing else. Okay, and security will say that if an attacker has a bunch of ciphertext and a bunch of secret keys, as long as the secret keys do not distinguish the ciphertext, the ciphertext should look pseudo-random to the attacker. So obviously, if f of x0 is different from f of x1, then of course that with this ciphertext has x0 and this has x1. But so long as that doesn't happen, security of your ciphertext should hold. So this is the notion of functional encryption. And it was shown by Anant Jain and Bitansky Vaikunthanathan that FE in fact implies IO. And let's look at what kind of FE suffices. So let's say that we're only supporting a single function key, but this function has long output. We want that the size of the ciphertext should be sublinear in the output length of the function. And let's say that we're happy as long as you simply support the function class NC0. Okay, so just constant depth polynomials, that's all. So how do you build this? I mean, if you have this, then you have IO, and moreover, you have FE itself, right? And FE itself is a very nice, useful primitive. So can we build this? So a natural idea here is to use the learning with errors problem, which has been used to build, the closely related primitive of fully homomorphic encryption, right? So let's remind ourselves how FHE works. The idea behind fully homomorphic encryption is that you can encrypt some message, let's say X. Think of a weak client as encrypting this message and sending it to an untrusted cloud for some computation. and this cloud can compute on this message while it is encrypted and get back an encryption of f of x, where f is the function that it computed. And now the client can decrypt the received ciphertext and recover f of x. So it sounds a lot like functional encryption, except that notice that this is all or nothing decryption, right? So the client has the secret key, so she can decrypt f of x, but she can also decrypt x itself. Okay, whereas in functional encryption, if you have a key for f, you cannot learn g of x. You can only learn f of x, and in particular, you certainly cannot learn x, right? So this is the difference between the two. So, but nevertheless, the fact that they are still both computing on encrypted data suggests that maybe the techniques are going to help us, and indeed they will, as we'll see, right? So FHE supports arbitrary circuits. It has compact ciphertext, which is independent of the circuit size that was evaluated, and it's very suited for all or nothing decryption, right? As we just said, if you just want to compute on encrypted data for all or nothing decryption, then FHE solves your problem. But when we try to use these techniques for functional encryption, which is asking for partial decryption, then in fact we end up with leakage, which is a security problem. And that's what we'll talk about next. Okay, so using LWE, you can certainly get the functionality that you want. You can compute on encrypted data. Just like in FHE, you can adapt those techniques and build new techniques to also support functional encryption, the functionality of it. However, the security guarantees that you get are very restricted. So in particular, FHE itself is, it's giving you all or nothing decryption. For FE, that does not suffice. So we don't know how to get the full game from LWE, but here are the kinds of restrictions that we can support. So either we can allow the attacker to just see a limited number of keys, secret keys, or we can say that you can see as many keys as you like, but they should be of a certain kind. So for Boolean functions, you should only have keys that evaluate the you should only have keys for functions that evaluate the challenge to 0 and not 1, for instance. Or you could use some combination of these, and you cannot do the general game. You cannot support the general game where the attacker can see any number of function keys of her choice, as long as the function keys don't distinguish the challenge. Not only do we not have a proof in the general security game, there are actually attacks against a scheme when an adversary is more general. So if the adversary moves out of these restrictions, then not only does the proof break down, in fact, you can break the security of the scheme. So there's even an attack. In fact, there are multiple types of attacks. So let's think about, or let's discuss the causes of attacks and what are the ways to overcome them. Okay, so let me describe some of the challenges that come up when you try to use LWE to build functional encryption and hence indistinguishability obfuscation. So one challenge is that the LWE keys are sort of inherently leaky. And let me try to explain what I mean by this. Okay, so first let's remind ourselves of the learning with errors or LWE problem. This is the problem of distinguishing noisy inner products from uniform. Okay, so if you have a matrix A and you have a secret S, then if you take the inner product or the matrix vector product of A and S and perturb it with a little bit of noise, for simplicity, you can think of this noise vector as simply being binary, although we can support more distributions. then the LWE problem says that this distribution is actually indistinguishable from A and the uniform distribution. Okay, so noisy inner products are indistinguishable from uniform. Okay, and when you build these FE constructions, you generally embed the learning with errors problem in your ciphertext. So your ciphertext looks like SA plus E, some avatar of that, and you use LWE to argue that, therefore it's going to be pseudo random and hide your message. So this is what our ciphertext looks like. And our secret key is usually coming from the short integer solution problem. So this problem is the following. Now, given a fact matrix A over ZQ, let's say, my goal is to find a low norm vector Z such that A times Z is 0 mod Q. Now, obviously, if you didn't have this bound on the norm, then this problem is easy to solve just by Gaussian elimination. But the fact that you have a bound on the norm and you're asking for it to be short makes this problem, in fact, quite hard to solve. Okay. However, if I have many of these short vectors, they actually form what we call a trapdoor for A. So if you have many vectors that are in the right kernel of A, then these form what we call a trapdoor for A, and these can be used to break LWE with matrix A. So the details are not important. I'm just trying to convey a high level problem in the LWE based schemes that we have when we try to take them all the way to functional encryption. So generally decryption works when these matrices match up, right? So you have SA plus E and your secret key is a short Z such that AZ is 0, for instance. This is all a gross oversimplification. But when these matrices match, at that point you can decrypt, and you can imagine how, right? So basically using this low norm vector Z, you can cancel out the SA part just by multiplying, just by taking the inner product of the ciphertext with the secret key Z, right? So the AS part will just get cancelled, and the error and the secret key will take their inner product. But because E is short and Z is also short, what you get in the end is still sort of small enough that it can be bounded. So in particular, this gives you a way to use this SA plus E as a mask for a message. So the Z will give you a way to unmask the message. Okay, so right now in my ciphertext, I don't even have a message, but I hope you can see that, well, adding the message is usually never the problem, right? So you can add a message in and figure out a way to decrypt. For instance, you can just add the message scaled by some very large scaling factor. And then when you take this inner product, if you get something small, the message was 0. If you get something large, the message was 1, because the noise contribution is very small and can be bounded. So what we need now is partial decryption capability. Okay, so let me try to walk us through some well-known ideas in functional encryption in the world of lattices. Again, only at a very high level. So now let's say that my encryptor computes some encodings of its input X. Okay, so some kind of LWE encodings whose exact structure is not important for us. So, the bit X1 is encoded using LWE matrix A1 and, up to Xn, which is encoded using AN. And the classic work of Bonnet et al. Showed that actually there is a way, if you design these encodings carefully, there is a way to evaluate a function on them. So this is just like fully homomorphic encryption, that you can evaluate on these encodings. You can compute a function on these encodings. But the nice thing is that the resultant ciphertext that you get, so suppose suppose that here I'm evaluating some function f on my encoding C1 to Cn. You can actually get an encoding under an LWE matrix that encodes the function f, and this is important. So you can get an encoding of f of x, but crucially under a public matrix which encodes the function f that you computed. All right, and this functional matrix here, right? A concatenated with AF. I mean, A is actually just hanging around. You need it for other things, but focus on AF. So AF is encoding your function f. This AF can also be computed just given the public matrices A1 to AN and F. Okay, so now if you have this, the rest of the ideas we saw already. Okay, so the key will just be the short vectors which maps this matrix to 0. And now when I want to decrypt, I can make use of the observation that, you know, the matrices in this ciphertext and this key, they now match. So I can decrypt and recover f of x. Okay, the catch here is that x is not hidden in this computation, but Gorbunov, Vakuntanathan, and we showed that, you know, in a restricted security game, you can also hide x. So in particular, what we'll do is we'll actually now hide x using fully homomorphic encryption. And when we compute our function, we want to compute a function f, we'll compose it with FHE decryption. So you get, you know, the FHE encryption of f of x first when you do your evaluation, and then composed with this FHE decryption, you can get you know, the encoding of f of x in the clear. And now even if these xi hat are revealed, so xi hat are the FHE encryptions of x, even if these are revealed, it's okay, because you know, these are now encrypted using FHE. But you do need to argue that this FHE secret key is hidden, because remember that when you do this function composition over here, when you do FHE decryption composed with F, then obviously that means you need the encodings of FHE secret key as well. And you need to argue that in fact this is going to be hidden. And this you can do in a restricted security game where the attacker cannot request any keys such that f of x is 1. So again, the details are not so important for us, but just suffice to say that if you want to hide x, you can use FHE on top of the you know, the construction we saw in the previous slide, but then you have to restrict your security game. So you don't get functional encryption, you only get a restricted class of it in a restricted game, as I already said. And there are attacks outside the game. And at a very high level, the idea is that, you know, if I get keys for linearly dependent vectors, then I can construct a trapdoor for a certain matrix, which can be used to sort of break the challenge. Okay, so maybe the details are not so important, but the main takeaway here is that this particular structure of keys, these short vectors that we gave out, as I described in the previous slide, these seem to have an inherent vulnerability, because they're, like I said, in the simplest case, you can put together these keys and construct a trapdoor. And once you have a trapdoor, you know, for the matrix in the challenge ciphertext, then all security is broken. And the attacks don't work in as simple a way as I'm saying right now, but by using some manipulations, you can reduce to that scenario where you can manipulate your challenge ciphertext, you know, to have some matrix B star, and you can manipulate your secret keys to have a trapdoor for some A star. And then if you have keys that are outside the security game, you can make these two matrices match. and break the security of the scheme. Okay, so any questions so far?
No, I think so far there are no questions. Thank you.
Okay, so what I argued in the previous slide is that, you know, when you have these lattice based techniques, then the structure of keys seems to be somehow inherently leaky, and this limits the security game that you can support, right? So so what should we do next? So one very nice idea is that let's try to combine lattices and pairings. Okay, so let's try to see how pairings might help in this situation. Since we talked about pairings, I mean, there must have been a point, right? So first, we have functional encryption for quadratic functions from pairings. Now this is not surprising because well, pairings, as we saw, they let you do degree 2 computation in the exponent. So you can, for instance, have a ciphertext for some vector x and a secret key for you know, some vector c, such that when you decrypt, you get the inner product of Cij xi xj. Okay. By the way, when I say that this is not surprising, I mean the proof is actually fairly subtle, but it's not philosophically, it's not surprising that, you know, pairings should let you do degree 2, and there are no restrictions in the security game. So this is one of the points I'd like to drive home. Okay, so with lattices you can get all this functionality. You can, you know, compute polynomial size circuits. So here this function f that we have in the key, this can be general, it can be, you know, any poly-sized circuit, but the security game is restricted, it's only one sided. On the other hand, with pairings, you're kind of stuck with just degree 2 computations, but the security game is unrestricted, and the goal is going to be to see whether we can get the best of both, and we'll certainly get more than a sum of parts, as you'll see. Okay, so what's going to be our idea here? So now remember that our lattice ciphertext, after evaluating the function f, had an encoding of f of x, the message f of x, under an LWE matrix A sub f, right? So once again, let's just think of A sub f and not focus so much on the A. So looking a little more closely at the structure of the ciphertext, note that the encryptor actually knows the secret S and the noise because the encryptor picked it itself, and it can provide a sort of linear, or well, quadratic, or even linear for that matter, ciphertext for this vector S comma noise. The key generator knows this matrix, right? So it can provide the key for this matrix comma 1, and linear FE is of course a special case of quadratic FE which we saw. So our decryption is going to recover the inner product of these two vectors. So the encryptor provides S comma noise, the key generator provides the matrix comma 1, and you'll recover to exactly get you know, this matrix times S plus F plus noise, right? And then you can subtract and get F of X, right? So this is something you can certainly do. So if I use a pairing based functional encryption scheme to implement this you know, this linear or quadratic functional encryption that we saw here, then it turns out the leakage created by LWE secret keys goes away, because in some sense I'm not giving you short vectors anymore. I'm computing on my ciphertext as I was doing before, right? So what am I doing now? This was my this is where I was, right? I knew how to compute this challenge ciphertext in this way, but I didn't know a good way to decrypt, because the way that I knew to decrypt using these keys was leading to security attacks, right? So what I'm going to do is I'm actually going to scrap this key generation, and I'll instead figure out a way to use pairings to give keys, right? So as I said, I'm just going to use my quadratic FE, which I can build using pairings and which supports both sides of the security game. And this is going to let me recover whatever I need to in order to subtract and get the message. So now what happens if I don't want to use pairings? Of course, that is the point of this talk, right? So we don't want to use pairings. We want to be post-quantum. We want to only use lattices. Now, in the previous slide, what I showed you did not even use the quadratic functionality. It was only using the linear functionality. And linear FE, in fact, exists from LWE, but it doesn't help us because it ends up having the same key structure that was giving us problems before. So there are other approaches from lattices, but they all suffer from an unsimulatable key structure, and they don't admit a proof from a well-chosen lattice assumption so far. So a challenge is to construct LWE-based FE with more secure keys. All right, so let me briefly talk about one more challenge. Let's even say that we have secure keys. Okay, so let us say that fine, for the secure keys part, we are using pairings. Are we done? Turns out, no, we're not done. And the reason is that what we discussed before is that even using pairings, we can recover something like f of x plus noise. By the way, there are really a lot of details that I'm brushing under the carpet just for the sake of presenting an overview of these ideas, right? So there's, for instance, a problem in how large this noise has to be. Anyway, so we won't talk about that in this talk. Let's just say that the decryptor recovers f of x plus noise, and it's supposed to throw away the noise and get f of x. But the problem is that this noise actually leaks too much information about x, because remember, this noise is the result of computing on encodings of x, right? So it leaks information about the original encodings, the original noise that was present in the encodings of x. So this is a problem. So one idea you could try is, flood this noise to wipe out the leakage. So just add to it a much larger noise so that this noise kind of gets wiped out. So how do we add this noise? So the first problem is that the noise would be too long if I were to just add it in the most naive way, and the FE scheme that you get will not satisfy the efficiency properties you need for IO. So an idea is that maybe I can use a pseudo-random generator. So use the seed in encrypt and expand this during decrypt. Now a problem arises that, I need a PRG in degree 2 to use with pairings, but then degree 2 is insecure. So there were a bunch of attacks that showed that. So the next idea is, can we flatten the degree of computation so that the public computation is high degree and private computation is of degree up to 2. So I have a deep computation I'm doing, but I'm breaking this up into a public part and a private part. I'm somehow squishing it on one side and, letting it expand on the other. So now this public part I can do kind of downstairs. I don't have to do it inside the pairing. And the private part I will do using the pairing. And this idea in different flavors has been used in functional encryption before. So once again, I'll do the deep public computation outside and shallow private computation using linear or quadratic FE. So, right. So I already said this, right? So I want to have this asymmetry in the depth of the computation. And now I also said, but let us recap, that FE for quadratic functions can be built from pairings, and FE for linear functions can be built from LWE as well as other assumptions. And linear functional encryption, is just a simplification of quadratic. So I have a vector X, I have a vector Y, and decrypt lets me recover their inner product. Instead of a quadratic polynomial, it lets me recover a linear polynomial of my choice. There are no restrictions in the security game. Okay, yeah, let's not worry about this for a second. So here is the last idea that I'd like to show you about flattening the degree. And this idea, it's a beautiful idea, which goes back to the work of Brzezinski and Vaikunthanathan in the context of fully homomorphic encryption. So let's just say that our ciphertext is this LWE sample plus the message, right? So C1 is LWE plus X1, C2 is LWE plus X2. Both of them are using S as the secret key. For simplicity, I'm thinking of one-dimensional LWE. So instead of the inner product of some vector U and S, I'm just thinking of scalar product. For some regime of parameters, this is also secure. And now I will, evaluate on these encodings. So because these are FHE encodings, I can evaluate on them. So let's see how to evaluate. Okay, so the first idea of BV11 is that let's take the decryption view. So instead of staring at the encryption and wondering how to evaluate on this, by the way, addition is totally trivial. I'm sure everyone agrees with that. You just add the two and you get an encoding of X1 plus X2. For multiplication, they said, let's take the decryption view. So let me write Xi as approximately equal to Ci minus UIS. So I'm just rearranging terms. And then let's multiply these equations. Okay, so I get this polynomial. Okay. Then they observe that actually this polynomial, you can break it into these components, right? So C1, C2, C1, U2 plus C2, U1 and U1, U2. And if you now let your secret key be 1 minus S and S squared, then the inner product of these two, in fact, gives you X1, X2 plus noise, which is what you wanted, right? So, now the same idea you can repurpose for the sake of functional encryption just by grouping the terms in this decryption equation differently. So now what we're saying is that let's remember we want to do the high degree computation outside and only low degree inside. So for simplicity, we're just looking at degree 2 here, where we do the degree 2 sort of publicly. So we compute C1, C2 publicly, and we use this inner product. So a linear functional encryption scheme will be used to compute the remaining terms. Okay. So now note that C1s, C2s, and S squared are known to the encryptor, and these other terms are known to the key generator. So if I give you a ciphertext for these terms and a secret key for these terms, just within linear functional encryption, I can take the inner product of these two, okay, add to it C1, C2 and recover X1, X2. So the key insight is that these cross terms, right, Ci, Cj, there are n squared of them. These can be done sort of downstairs. And this linear equation alone needs to be sort of evaluated in a private way. And this can be generalized to NC1 circuits. So I'm running out of time. Let me just wrap up with this idea. So in the last slide, I showed you how to reduce, the computation to linear, but this is actually too much leakage. It turns out that if you only reduce the computation to have degree 2 in the secret terms, then the adversary sees quadratic equations in the secret terms. And this you can conjecture to be secure using something like a multivariate quadratic assumption on some distribution. So this is the weak LWE with leakage type of assumption. And what JLS21 do is they use very interestingly the notion, the assumption of learning parity with noise to somehow resolve this leakage. So we don't have time in today's talk to go into it, but certainly if I had quadratic functional encryption from LWE instead of linear, then possibly I could also use LPN in a similar way and get a post-quantum version of FE and then IO. But this problem seems to have some significant technical barriers. So yeah, just to summarize, we have to figure out how to strengthen LWE keys, how to generate this smudging noise, and can we leverage the fact that the noise value need not be computed exactly? Even if it is only approximately correct, it still serves the purpose. So I don't know if approximate correctness is going to help us in some way. All right, so let me just conclude with some open problems. So first of all, can we replace pairings with some weaker structure that we can build from LWE? Can we have new, simpler, plausible assumptions from lattices that chart this territory between LWE and multilinear maps? Can we improve lattice-based multilinear maps or build post-quantum FE and applications from that? Can we use LWE for applications of IO, even if not IO itself? So for example, deniable encryption. So these are some of the, outstanding open questions in the area. And there are, of course, many, many more. So with that, I'll thank you and take any questions if there are.
Thank you very much, Shweta, for this very interesting talk. Captivating from the first to the last slide. Thank you very much.
Thank you, Nina.
So I encourage the audience to ask your questions. And I would like to start with a rather technical questions. This is actually also going into one of your open questions, where you said to replace pairings with lattices or with a lattice-based construction.
Yeah.
And you said, if I understood correctly, you said that there exist already constructions, but the proof seems to be challenging.
Yes.
Can you summarize? Can you summarize or give an intuition why the proof is challenging?
Yes. So first of all, if I want to do quadratic function, like I want to do quadratic functions using these encodings, one approach is to use these encodings with structured noise. So in a way, when I multiply the encodings, I want the noise terms to live in an ideal that annihilates with the sort of the public, not matrix anymore, the public polynomial. Like you can go to an n-true setting, you can go to an n-true setting and you can set it up so that your encodings have, noise that lives in a secret ideal. So they're not picked from the whole space, but just from some secret ideal. And in this way, you can kind of handle the noise blow up that would happen otherwise. But then the problem is that finally, when the attacker decrypts, she gets to see a large, let's say, some high degree polynomial in these weird noise terms, right? And this is supposed to mask the message, correct? The problem is that these noise terms, in fact, contain within them these secret ideal terms. So there's no attack that we know of. But the reason you don't get a nice proof is that you kind of mixed up your PRG with your encodings, right? So first of all, you're using n-true in a non-standard way. And moreover, you're mixing up this n-true style assumption with a PRG style assumption. So you're you can't separate them nicely in the way that JLS21 do.
I see. Right. Thank you. And so in your talk, you talked a lot about how to build post-quantum IO from FE.
Yeah.
But you also mentioned two other approaches, one of them also being
Yes.
functional encryption, and I unfortunately forgot the third one.
Yeah, the second one is actually this notion called functional encodings or succinct randomized encodings. And the third one is FHE with some sort of strong circularity guarantees. So both these lines are very promising. In fact, if IO alone is your goal, then these lines may even be more promising than the one that I discussed, because these primitives are weaker than functional encryption. So, like for instance, functional encoding, you can think of it like a kind of single ciphertext functional encryption scheme, where the yeah, I mean there's only one ciphertext that the key needs to work with, so it's a lot less constrained than functional encryption in that sense. But it's also incomparable. I mean, it just seems weaker. I don't know, at least off the top of my head, if it if one implies the other, but it just seems weaker. So the succinctness, the shortness requirement on the ciphertext is different. But it just seems easier to construct. So there are a couple of works that construct this again from non-standard assumptions, but yeah, there is some sort of you can do more with that, and similarly for the third one.
I was in particular interested because, I mean, FE, as you also said, it comes with these limitations on the security models, right? That I think you called it.
No, that's only what we can achieve. I mean, what we're trying to get to is, of course, the unrestricted model. So I was
and I was wondering if this is also in the other approaches, if there's a similar restriction or a similar, or not restriction, a similar limitation or not.
No. So also in the structured noise approach, that limitation is not there. I was, maybe I should have emphasized this more. The restrictions I was talking about are restrictions that exist when you have a provable reduction from LWE. Right? So if you want to base it on LWE, then at the moment we have these restrictions. If you start relaxing, your assumptions, like if you take these funky intro style assumptions, or if you settle for functional encodings, or this FHE with circularity, then you can construct IO via a different route, of which is called XIO. So it's a different route. So it seems weaker than going via functional encryption.
I also have one, maybe to wrap this up, one more general question. And it's actually about your very first slide, where you had this very nice graphic with the three different colors. And I was wondering, what do you think is the most promising one that kind of moves to the inner circle? So is there one that's most promising, moving from red to yellow, or maybe from yellow to being practical?
So that's a great question. I'm trying to go back to my slide.
And then also I was wondering, if we move towards the practical green circle, I mean, now there's, of course, the NIST standardization going on, but there's also the ETSI identity-based encryption standardization going on. Is there even hope, or what would be the most important next one of the, let's say, advanced cryptographic primitives? I mean, you also worked on these other advanced encryption schemes. Is there maybe one that is most pressing to also be standardized, or is there hope for one to be standardized soon?
So actually, I'm not maybe the best person to know about which is the most pressing one to be standardized. But one area that I've been looking at in this context recently is before that. So I think these zero knowledge proofs for certain algebraic statements is a very nice candidate. And another area, going back to what I started, another area that I've been looking at are, these different types of signatures, like blind signatures, threshold signatures. So especially blind signatures, I think that they're a very important primitive with lots of applications. And in the post-quantum world, we have very little that we know about them. We have some very nice feasibility results again, but they're not practical. So recently I've been interested in how to make these blind signatures practical. So I think that's something which, maybe the community can take forward and give us something which is genuinely practical. We do have one new candidate, which is based on a new assumption. Since it's a practical oriented scheme, we felt that a new assumption is justified here. And either that or some improvements, it would be great to see. But I mean, there may be so many other primitives that I don't really know that much about.
All right. Thank you so much again for the talk and the discussion. Unfortunately, our time is up, but please feel free to continue the discussion also in the networking chat. So next there is a break.
That? Okay.
The network chat for everyone is when you are on the LatinCrypt platform. I think on the bottom left, you can click and then chat with participants. And we are taking a break now. And please join back for the next session in about 25 minutes at 11:30 Colombian time. Thank you so much.
Thank you.